Hi guys, so today we're doing the last lesson in chapter 4, which is lesson 4.5. We're going to learn how to solve polynomial and rational inequalities today. And in chapter 4, up until this point, we have talked a lot about polynomial functions and rational functions. So now we are just going to switch gears ever so slightly and talk about their inequalities. Okay, so for today's warm-up, you're going to find the domain and the horizontal asymptote of this rational function, which is from last class's lesson. So as a reminder, when you're finding the domain of a rational equation or rational function, you take the denominator and you set that not equal to 0, because we know that we cannot take any number and divide it by 0 because that is undefined. Okay, so that determines what the domain is going to be here. So we know x minus 2 quantity squared cannot equal 0, and then we solve for what x can't equal. So I'd have to square root both sides. Square root of 0 is just 0, so I get x minus 2 can't equal 0, and then I would add 2 to both sides, which would tell me that x cannot equal 2. Okay, so x can be any real number except for 2. So if we were going to write this in interval notation, that means it could go from negative infinity to 2, not including it, and 2 to positive infinity. So that would break up the interval there into 2 separate ones. Okay, and then the horizontal asymptote, which I'm going to abbreviate. Remember, for that, we have to look at the degree of the numerator and compare that to the degree of the denominator. To find the degree, we look at the exponent. And so here, for the numerator, we don't see a variable. We look at the exponent attached to the variable. There's no variable here, so the degree is actually 0. And this is the same thing as writing 1 times x to the power of 0, because x to the power of 0 is also just 1. So that's where that degree 0 comes from. All right, and we call that n, degree 0. I always remember n for numerator. And then the degree of the denominator is 2. We call that m. And then we compare them. So n, 0, is less than 2, which is m, okay? And because n is less than m, that tells us the horizontal asymptote is at y equals 0. All right, so definition of a polynomial inequality. Super simple. It's just a polynomial that is in the form of an inequality. So if we call the polynomial f of x, we have that entire polynomial to usually the left side is where we want to write it, or the right side, and then we have 0 on the other side. So it's either less than 0, greater than 0, less than or equal to 0, or greater than or equal to 0. So let's actually go through the steps for how to solve a polynomial inequality, and then we'll do one example and move on to rational inequalities. So step number 1, just like I showed you back here, you want to get the polynomial on one side by itself and 0 on the other side. So that's exactly what step number 1 is. We want to get f of x, the polynomial, all on one side. So in this case, I would need to subtract 20 from the right side. I'd get x squared minus x minus 20 is greater than 0. Okay, so that is my polynomial right here, x squared minus x minus 20, and now it is nice and neat. It's in this form, 0's on the other side. Okay, then we take this f of x, the polynomial, and we actually set it equal to 0. So even though we need to find where is it greater than 0, we're going to set it equal to 0 for the second step. So x squared minus x minus 20 equals 0, and we're going to solve for what x equals. So we treat it like it's a normal polynomial equation. In this case, this is a quadratic, and oftentimes these polynomials are going to be quadratic, so you're going to have to factor them. Okay, so we need x times x to give us this x squared. Then we're looking for 2 terms that multiply to give us negative 20, and add to give us this middle term of negative 1. So negative 5 and 4 will do that. Okay, so this is in factored form. Then we use 0 product property. We split the factors up. I'm going to do that over here. Set x minus 5 equal to 0. Set x plus 4 equal to 0. And then we solve both for x. So here we'd add 5 and then here we would subtract 4. So we'd get x equals 5 and x equals -4. Okay, so we're not done. If this was an equal sign right here, then we'd be done. But it is an inequality symbol, and we need to know when is this inequality greater than 0, not equal to 0. So what we just found here are the boundary points of our solution, okay? And these boundary points, we're going to locate them on a number line. So our boundary points are +5 and -4. Now, these boundary points are where, in essence, the inequality to this solution is going to start or stop. So it's going to start or stop at -4 and at +5, and both of those are going to be open circles or holes because we know that this inequality symbol is just a greater than symbol, so it can never equal these specific boundary points. It's just going to be greater than these boundary points or less than them or between them. So we need to figure out where the inequality actually points for the solution. Is the solution here to the left? Is it in between them? Is it to the right? And so we're going to do that next, okay? So after you locate these points on a number line, which I'm going to just transfer over here and show you guys, then what we have to do to get our final solution is we need to actually test some values within each interval that is created on our number line. Okay, so again, we have -4 here, one boundary point, 5 here, one boundary point. They're both open circles because the inequality symbol is just a greater than symbol. So we need to test a value to the left of -4. So I'm just going to pick -5. Could be anything that's less than -4, so I'm going to pick this. I need to test a value between the two, so let's just pick 0. So between -4 and 5, it could be -1, it could be +1, -2, +3, anything like that. And then I need to pick one on the other side of this interval, so to the right of 5. So let's just pick 6. Okay, and when I say I test these numbers, what I mean is I'm going to plug them in to the inequality, and I'm going to see if it makes the inequality true, because I'm trying to figure out where is x squared minus x minus 20 actually greater than 0. So I'm going to plug this number in for x to see, okay? So plug in -5, -5 squared, always put it in parentheses, minus -5, plug it in for x minus 20, and I'm trying to see, is this in fact greater than 0? So that's why I put a question mark over it. So -5 squared is 25, minus negative is a +5. So we get 30 minus 20, which is 10. And then I checked to see, is 10 in fact greater than 0? It is, okay? So what that means is since -5 is a solution to this inequality, every number that is also in this interval, so to the left of -4, should be a solution. Okay, so that's going to be part of my solution, is everything in this interval right here. Then I go on to test the next value. So test 0. So I'm going to plug 0 in for x here and here. So 0 squared minus 0 minus 20. I'm trying to see, is that greater than 0? This is 0, this is 0. So is -20 greater than 0? Nope, it is not. -20 is definitely less than 0, which means that if 0 is not a solution to the inequality, none of the values between -4 and 5 are solutions. Okay, so we cross this out. This interval doesn't work. I'll still let you see it for now. And then finally, we're going to test 6. So plug this in. So 6 squared minus 6 minus 20. See if that's greater than 0. So we get 36 minus 6 minus 20. And I'm just doing this really quickly. But you guys can also do a lot of this in your heads or using a calculator to help you. Okay, so we get 10 is greater than 0, which it is, again. Okay, so then what this tells me is that any value to the right of 5, as long as I did my math correctly, any value to the right of 5, that's also a solution. So everything in this interval is a solution. Everything in this interval is a solution. So that means my final answer or interval is from -4 to -infinity and +5 to +infinity. So you draw that on the number line, The other thing you could do, remember, we can put parentheses here. Okay, that's a little bit more formal, college algebra-like. And then the final step, number 5, is you have to actually write the solution set. So negative infinity to negative 4 is this part of the interval, and then 5 to positive infinity is the second part of the interval. And so that's the actual solution. And that, again, you only are going to get that solution after plugging in these boundary points. Okay, so let's now practice a second example now that we know the process. Also, just something to note really quickly, this procedure totally works the same, and these steps are the exact same if instead of having just like a less than symbol or a greater than symbol, you have less than or equal to or greater than or equal to. The only difference is that if it can actually equal it, that means the boundary point is going to have a point at it instead of an open circle like ours did, because that means it can actually equal that boundary point. Okay, so solve and graph this one. First step, step number 1, like we said, is we need to get the polynomial to one side and 0 on the other side. So I'm going to subtract the 10x. So I get x cubed minus 3x squared minus 10x is greater than 0. Okay, so now 0 is on one side, and then I have got my entire polynomial on the other side. Usually I like to move it to the left side. Step number 2, we set the polynomial equal to 0, and we solve for x. Okay, so I'm going to notice here there's a greatest common factor between all of these. This is a third degree polynomial or a cubic function. So I'm going to factor out an x from each term, which would leave me with an x squared minus 3x minus 10. Okay, and then I'm going to also factor what's left in the parentheses. So all things quadratics are coming back. All right, I'm looking for two numbers that multiply to give us negative 10 and add to give us negative 3. So negative 5 and positive 2. So x minus 5, x plus 2. Okay, 0 product property, split these up, set them equal to 0. You get x equals 0, 5, and negative 2. So these are my boundary points. Okay, step number 3, I'm going to erase this real fast. Step number 3, we set it up on a number line. Excuse me. All right, so here's my number line. Gotta set up 0. Actually, let me move it over a little bit. Negative 2. And positive 5. Okay, now because this is, again, just a greater than symbol, all of these boundary points are going to be holes. Okay, so I put a hole here, here, and here. And now when I create my table to test these boundary points, I'm going to have 4 intervals. So to the right of negative 2, in between negative 2 and 0, in between 0 and 5, and then to the right of 5. Okay, and I like to make my table or set it up right below the number line. That way I can really easily see the intervals that I'm looking at here. So I need to look to the left of negative 2, so let's just test negative 3. Okay, in between negative 2 and 0, so let's test negative 1. In between 0 and 5, so let's just test 1. And then over to the right of 5, so let's just test 6. Okay, then I go back here to step number 1, and I look to see what the polynomial inequality was, and I plug all these values in for the x's in the equation. Okay, so I need to see, is negative 3 cubed minus 3 times negative 3 squared minus 10 times negative 3, in fact, greater than 0. Okay, so I'm going to simplify this. This is where you might want to grab out a calculator just to help you out a little bit. So negative 3 cubed is negative 27. And then minus 3, negative 3 squared is 9. Minus 10 times minus 3 is positive 30. Then this gives us negative 27 minus 27 plus 30, and all this gives us negative 24. We're trying to see, is this greater than 0? Nope, definitely not greater than 0. So that interval is not a part of the solution set. Okay, then we check the next one, so test negative 1. So negative 1 cubed minus, again I'm plugging this in for x, minus 3 times negative 1 squared minus 10 times negative 1. And super, super important, again, you guys, that you use parentheses here. So negative 1 cubed is negative 1, minus 3 times negative 1 squared is 1, and minus a negative becomes a positive. So you're left with negative 1 minus 3 plus 10, which gives you 6. Is 6 greater than 0? Yes, it is. Okay, so this is going to be part of our solution set right here. We know for sure it's going to be in between those values. Okay, keep going. Test number 1. So 1 cubed, whole process. I'm just going to zoom through this. Okay, so this is 1 minus 3 minus 10, which is negative 12. Negative 12 is less than 0. It's not greater than 0. So that interval does not work. Okay, and then last but not least, test 6. So I plug in that 6. I get 216 minus 108 minus 60, which is going to give me 48, which is in fact greater than 0. Okay, so this is another part of my solution set. So from 5 to positive infinity. Okay, so then we write our final answer, step number 4. So we look at the intervals. This is from negative 2 to 0. And then this interval is from 5 to infinity. And both of them are parentheses because we know that the original inequality was just a greater than symbol, not an equals to symbol, so these can't be actual points. If it was an equals to symbol, then they would be points like so. And again, another way to write this or to draw this is using those actual parentheses, like that. Okay, so that's how to solve a polynomial inequality. Now let's quickly talk about rational inequality. So rational inequality is a rational that looks like this, P of x divided by q of x with an inequality symbol. So same thing, less than 0, greater than 0, less than or equal to 0, or greater than or equal to 0. With the knowledge, obviously, like we just talked about with rational functions, that the denominator can't equal 0, because if you ever have a number divided by 0, it is undefined. Okay, so that is a given. All right, so let's just jump right into solving. So step number 1, same thing here. We're going to have to express the inequality so that one side is 0 and the other side is a single quotient. So here I would want to subtract 1 from both sides. And then this is going to be a little bit more challenging because I'm going to have to combine the fraction. So I have 2x over x plus 1 minus 1 is greater than or equal to 0. Now, this obviously is what I want. I want 0 on one side, but I need to combine these. And the way that we add or subtract fractions is we get a common denominator. So I take a look. This is my denominator over to the left. This one has a denominator of 1. So my common denominator is going to be x plus 1. So I need to multiply the negative 1 by x plus 1 over x plus 1. That's all greater than or equal to 0. Okay, so here I'm just going to distribute this negative 1 times x plus 1. So I get 2x minus 1x, and then minus 1 times 1 is minus 1. And I'm going to combine this. Now I have a common denominator, so I'm going to combine this, and I get this all divided by x plus 1. Or if you want to write this out in an in-between step, we have 2x minus 1 times x plus 1. All divided by x plus 1 is greater than or equal to this. Distribute. Okay, And then we're just going to simplify as much as possible. So I look and see, do I have any like terms? Yep, 2x minus x gives us just x. So I get x minus 1 over x plus 1 is greater than or equal to 0. Okay, so that's step number 1. You want to combine it into a single quotient, meaning a single fraction. No fraction plus or minus number. All right, once you've done that, which oftentimes that's the hardest part, this is what we got, then you set the denominator and the numerator equal to 0, and you solve, and those are your boundary points. So we take the numerator, x minus 1, set it equal to 0, and the denominator, x plus 1, and set it equal to 0. And those are our boundary points when we solve. So we'd add 1 to both sides, we get x equals 1, subtract 1 from both sides, x equals negative 1. Okay, and then step number 3 is same as a polynomial inequality. We are going to locate those boundary points on a number line and divide the number line into intervals. Now, the one thing that we need to say at the very, very beginning, which I forgot to do, is what the restricted value is when we get to this point, okay, where we have a single quotient or a single fraction. So we need to write down the restricted value or the domain, okay, of this inequality. We noted that the denominator cannot equal 0. So looking back here, x plus 1 cannot equal 0. This becomes really important when we're solving because we need to make sure that we account for that. And so if we subtracted 1 from both sides, that would mean x cannot equal negative 1. That's the one value it can't equal. And the reason I want you to make sure you always do this at the beginning or after you have this single inequality is so that you don't accidentally put that as one of the values when you find your boundary points. Okay, so take a look. X cannot equal negative 1. We just said that, right? And this, one of your boundary points, is negative 1. So even though this is a greater than or equal to symbol, what we need to account for on the number line is that x can't equal negative 1. So on the number line, when we locate our two boundary points, we would have positive 1 and negative 1. Positive 1 could have an actual point there, but negative 1 would have to have an open circle because of this restricted value, knowing that it can't actually equal negative 1. Okay, but positive 1 can because this is a greater than or equal to symbol. So just be really, really careful of that. Okay, so 0, negative 1, positive 1. Again, we've got a closed circle here and an open circle at negative 1. Just want to make sure I did that correctly. Yep. All right, so then we're going to do the same thing that we did with polynomials. We pick boundary points. So I'm going to pick something to the left of negative 1. So let's just pick negative 2. Something in the middle, so let's pick 0. And then something to the right of 1, so let's pick 2. Okay, and then again, you want to make sure that you're going back to what the original inequality was when we got it to be a single fraction. So x minus 1 over x plus 1 is greater than or equal to 0. All right, so plugging in negative 2 for our x's, we'd get negative 2 minus 1 over negative 2 plus 1. We're trying to see, can this be greater than or equal to 0? So negative 2 minus 1 is negative 3. Negative 2 plus 1 is negative 1. So divide those, we get positive 3. Is 3 greater than or equal to 0 then is what we have to evaluate, which it is. So that means this is going to be part of the solution, pointing this direction. Okay, test 0. So plug it in, 0 minus 1 over 0 plus 1, which is just negative 1 over 1, which is negative 1. And negative 1 is not greater than 0. Okay, and last but not least, let's test 2. So 2 minus 1 over 2 plus 1, so 1 over 3. Is that greater than or equal to 0? Yes, it is. Okay, so this interval also is a solution. And then we write down our final answer. So we have the interval from negative 1 here to negative infinity. and then from positive 1 here to positive infinity. So negative infinity to negative 1, not including it, our U symbol for union, and then 1 including it, so bracket, to infinity. So again, the way that we like to draw this for college algebra is using parentheses and brackets. So parentheses here, brackets here. Okay? And then last example right here, I'd like you guys to try this one on your own, and then you can come back and take a look at it. So step number 1, we would subtract the 3 from both sides. We'd get 2x minus 7 over x minus 5 minus 3 is less than or equal to 0. Okay? Then we need to get a common denominator. So I know that that's going to be the x minus 5. So I would multiply this by x minus 5 over x minus 5. Okay, I'm going to combine this, now that I have a common denominator, into one numerator, all divided by x minus 5. Remember, you only write that common denominator once, is less than or equal to 0. And then I need to simplify. So I'm going to distribute this, so 2x minus 7 minus 3x plus 15, all divided by this. Okay, keep going. I'm going to write this up here. Combine my like terms. So 2x minus 3x is negative x. Negative 7 plus 15 is 8. All over x minus 5 is less than or equal to 0. Okay, so now step number 2. Since I have a single fraction, I'm going to take each part of the fraction, set it equal to 0, and solve. So here, if I added x to both sides, I would get x equals 8. That's one boundary point. And then set x minus 5 equal to 0. If I add 5 to both sides, I get x equals 5. And that's another boundary point. Okay, step number 3, we locate these boundary points on a number line, and we need to check for restricted values. So I take a look here at my denominator when I had a single fraction, and I note the restricted value is that x cannot equal 5. Because if I plugged in 5 here for x, 5 minus 5 would give me 0. Okay, so that means right here, this boundary point is going to have to be an open circle. So I graph 5, 6, 7, 8. So 5 is an open circle, 8 is a closed circle. And then I make my little chart here for the intervals, and I'm going to plug in a couple values. So let's test. Oopsies, got to check off the shape editor. Let's test 4, 6, and 9. Actually, let's test for this one. Let's test 0, because 0 is also on this side of 5, and that's a little bit easier to work with. So whenever we can, I like to plug in 0. Okay, so we're going to plug that back in to this guy. All right, so negative 0 plus 8 over 0 minus 5. And then this is 0, this is 0, so 8 over negative 5, which is just negative 8/5. Okay, and we are trying to see, is this less than or equal to 0? Yes, it is. It is less than or equal to 0. It's a negative, so pointing this direction. Okay, test 6. So 6 plus negative 6 plus 8 over 6 minus 5. So this gives me 2 over 1. Is this less than or equal to 0? No. 2 is greater than 0. Okay, and then 9. So negative 9 plus 8 all over 9 minus 5. So this gives me negative 1 over 4. That's a negative, so it's less than or equal to 0. And that means that the rest of our solution is going to point this direction. Okay, so then our two intervals are from negative infinity to 5. I almost said negative 5. not including that, and then 8 to positive infinity, including the 8. So again, just make sure on these rational inequalities, you have to check that restricted value, and I will say a lot of times one of your boundary points ends up being that restricted value. So make sure you check it so that at that point you don't actually have a point there, you have just a hole or an open circle. All right, so that is 4.5. You guys can go ahead and get started on the homework.